Okay, so here's the first part of homework 7-2. We'll go ahead and just jump in with this. So, first question, there must be equal amounts of mass on both sides of the center of mass or the center of gravity of a system. Okay, so your intuition on this one might actually kind of lead you astray, because you think if it's balanced, right, if the center of mass is in the middle, then surely there has to be the same amount of mass on both sides. However, I want you to keep in mind that as we calculate the center of mass, two factors come into play: the position of that mass and then the mass itself. Okay, so if we think about this, if we think about, for instance, like a diagram here where maybe you have a large block on one side and then a smaller block on the other, the center of mass could very well be between those two blocks. If you look at either half of this diagram, if you look at either side of this center of mass here, you definitely have a lot more mass on the left-hand side, right, than you have on the right-hand side. So just because the center of mass is the central location does not mean that it divides the two masses equally. If we look at kind of the average distance away from the center, the average distance to the mass over here is going to be smaller than the average distance to the mass over there, and that's why this still finds us the center of mass. Okay, so this one again, maybe one of the trickiest ones in the true-false ones here, but it is actually false. The center of mass does not have to divide the object into two masses. Question 2 says two forces produce equal torques on a door about the door hinge. The first force is applied at the midpoint of the door, the second force is applied at the door knob. Both forces are applied perpendicularly, so we know we're getting the full force since they're applied perpendicularly. Which force has a greater magnitude? Okay, so it tells us that they have equal torques, right? And that's the key to this relationship. We know that you've got two forces. Here's my door, here's the hinge on the left-hand side. Two forces are being applied at the door, one at the midpoint, one at the end of the door. Okay, so one at the midpoint, one at the end of the door. If they were to produce the same torque, we have to consider what comes into play, right? So we know that they have the same torque, but torque isn't a factor of just the force itself, right? Torque is related to both force and the distance from the center of axis. Okay, so if I look at the first force in the first radius and compare it to the second force in the second radius, well, the force applied at the midpoint of the door is going to have a much smaller radius, right? It's going to have half the radius of that at the doorknob itself. Okay, so if I cut the radius in half, but I want to produce the same end result, then this force is going to have to be much stronger to keep this left-hand side of the equation balanced, right? Okay, so if I want to have the same torque, but cut the radius in half, I'm going to have to compensate by having a much higher force. So the force that is acting at the midpoint is definitely going to have the higher force to produce the same torque as something further out. Question 3 says, as shown in the figure, a given force is applied to the rod in several different ways, so it is the same force in each of those diagrams. In which case is the torque about the pivot point P due to the force the greatest? So we're asking again, in which situation is the torque going to be the greatest? So again, things we have to keep in mind are torque equals force times the distance, and then it is important that we think about the fact that there's possibly an angle involved for some of these forces, right? So we get the maximum torque when the force is applied at a 90-degree angle, when it's applied perpendicular, right? So in general, we're looking for when is the force applied perpendicular to the lever arm, and in this case the door. Okay, so if it's a sine of 90 degrees, that would just be 1. So really in that situation, if I'm kind of thinking that through, if I was comparing, for example, 1 and 4, I would know that 1 would produce a much higher torque than example 4, since 4 is at an angle, so that helps me rule that one out. 5 would produce no torque, since I'm pushing straight into the hinge, right? I wouldn't cause any rotational motion. 3, if you look at that, even though it's a relatively small angle, it still does make an angle with respect to the perpendicular. So once again, compared with the original one, it's going to be less than the torque produced by the first one here. So then the question becomes, okay, does 1 or 2 produce more torque? Well, as we've seen in the last couple problems, torque is dependent on both the force and the distance, right? So if the distance is cut in half, then that generates a torque that is cut in half as well. Okay, so that helps me rule out 2, so question 1 has to have the highest torque generated about pivot point P. So the last question on this first page here, question 4, is another good one to help us avoid maybe generalizing too much. So if the sum of the external forces on an object is 0, the sum of the external torques on it must also be 0. What we're going to see here is that the force and the torque are not necessarily directly related. Okay, so let's go back to the door type problem we've seen a couple times now. If I've got a door that's rotating about a pivot point, if I apply a force of 10 newtons here and a force of 10 newtons at the far end of the door, if we look at the net force would be 0, right? We'd have positive 10 newtons going up, we'd have negative 10 newtons going down, so my net force would in fact be 0. But because, once again, torque comes into play where we have both the force and the radius, right? Since these forces are acting a different distance away from the axis of rotation, we see that no matter what those distances are, the torques produced would definitely not be the same since they have the same force and a different radius. So the torque generated by my first force would not equal the torque generated by my second one, and therefore there's no way that the total sum of those can be 0. Okay, so just because the net force is 0 does not mean that the external torque also has to be 0. And so that one's a false statement. Could it happen? Absolutely. Right, if we had a 10 Newton force over here and a 10 Newton force directly opposite of that with respect to our lever arm, then absolutely our torque could happen to be 0. But it doesn't have to be, and that's the big question here. So question 5 is actually just a review question for us, right? It goes back to momentum, so 3.45 kilogram ball moving to the right at a speed of 2.50 meters per second, smacks head-on into a 4.00 kilogram ball that is initially at rest. The first ball ends up moving with a speed of 1.20 meters to the left, and the direction here is the biggest thing you have to watch out for. So it ends up 1.20 meters per second to the left. What is the velocity of the 4.00 kilogram ball after the collision? Okay, so we know in any collision, momentum is conserved. Right? The total momentum beforehand has to be equal to the total momentum afterward. This isn't a terrible collision problem because if we notice, both directions here are all linear, so it's right is moving to the right and then left to the left. We don't have anything moving up or down, which simplifies the calculation, right? We really only need to worry about, for our horizontal measurements, conserving momentum. Okay, so what that tells me, if I'm kind of thinking this generically, right, momentum is m times velocity. So I have two objects possibly moving before the collision. I've got mass 1 times the velocity 1 plus mass 2 times velocity 2. Now we know the second object before the collision is at rest, so this will ultimately simplify, but it doesn't hurt to account for that, right? And then after the collision, we know for sure the first ball ends up going backwards, so m1 times velocity 1 final plus m2. And obviously they're indicating that we want to find the velocity, so this is not going to be 0 over here, but we need to find our final velocity for the second. So if we take the time to set this one up, not too bad. Again, maybe just been a little while since we've seen momentum, but at this point, simply plugging in the numbers, we'll find that the only variable that we have is the second velocity, the second final velocity. So plugging in 3.45 times the velocity of 2.50, and I am defining that as positive, which means I'm defining the right as positive. Again, I know that my second mass is initially at rest, so I'm going to go ahead and negate this. I'm going to cancel this out since I know I'm multiplying it by a velocity of 0. Okay, so I'll go ahead and just throw that in as a 0. And then equals my first mass of 3.45. And again, here's the biggest step, here's the biggest thing to watch out for. We need to make sure that because the velocity is now going to the left, we use a negative velocity, so a negative 1.20, and then plus my second mass times its final velocity, which is, again, the only variable we have. So at this point, just simple algebra, right? Make sure you're careful in solving for this, right? I'd add this quantity over to the other side since ultimately this is going to be a negative number. I get it to be about negative 4.14. On this side, it's 8.625. So then adding the 4.14 over, and then obviously dividing by 4 once I get that, to get that by itself. So the final velocity that I end up getting for the second object is 3.19 meters per second. And since they do ask me for velocity, I should try and indicate the direction. Since this is positive, I know that this must also be moving to the right. So that's, again, going back, most of us I know are pretty comfortable with it, but it doesn't hurt to see one of these. So for question 6, they tell us Pluto, obviously the planet, has a mass of 1.2 times 10 to the negative 22nd kilograms. Mean distance between it and the Sun they give us the radius there. The mass of the Sun they give us as well. How long in terms of Earth years is a Pluto year? Okay, so they're asking us for the length of time, right? So they're asking us for the period. Is a Pluto year compared with that of an Earth year? Well, two ways we can work this problem. The easiest way is if you remember your formula for orbital period, right? We know that orbital period would equal 2 pi times, and again, it's been a while since most of us have done this, but it'd be r cubed over g times m. The toughest thing to remember, obviously, is this formula. You don't get the formula on the formula sheet. You have to know where this comes from. And then the other question that sometimes comes up is, which mass do I need? Well, anytime we're using calculation for orbital velocity or period, we want to make sure that this is the planet that we are orbiting around, right? So this is the planet that we are orbiting around, the mass that we're orbiting around. So in this case, it would be the Sun. It's not the object itself. It's not the object in orbit. Okay, so you remember this equation, it's awesome. Just plug it in, right? Solve from there. The other approach, though, that we do need to be pretty comfortable with is, where does this equation come from? Because probably a lot of us come AP test time aren't going to remember this equation. Okay, so instead what we can do is try to remember the relationship that this comes from. Well, you've got the Sun, then way out here somewhere you've got Pluto. Right? Pluto's following a roughly circular orbit. Right? Obviously it's more of an ellipse in real life, but at least to a degree it's going to be semicircular. Okay? And if we know if something's moving in a circular orbit, it has to have a centripetal force. Okay? So then the question becomes, what's providing the centripetal force? Remember, the centripetal force never exists on its own. It always has to come from something else. In the case of orbit, the only other thing that can be providing the centripetal force is the mutual force of gravity between, right, the planet and the Sun. Okay, so there's this force of gravity between that's pulling those two towards each other. That's the only thing that's providing my centripetal force. Okay, so as long as I recognize that, I can set my centripetal force equal to my force due to gravity, and then it just comes down to knowing these equations. Well, the good news is you do have these equations at least pretty easily found on the formula sheet. Now, they don't give us centripetal force, but we know force is mass times acceleration, and they do give us a centripetal acceleration. Okay, so looking that up, this is mv squared over r. We want to use the universal law of gravity since we have two masses that aren't the Earth. Okay, so we don't want to just use mg, but we want to use g, m1, m2 over the distance between them squared. Okay, so at this point, if we look at it and simplify it down a little bit, one of the radii cancels out, and then the mass of Pluto would cancel out. And this allows me to solve for the orbital velocity, right? So I can solve for the orbital velocity by using my universal constant for g, the mass of the planet, and the radius between the two. Okay, so I can pretty easily do that. I can pretty easily solve for the orbital velocity. Once I have the orbital velocity, then it becomes, how can I use the orbital velocity to help me find the period, right? So now I need to be thinking, okay, how does this velocity help me with the period? Well, again, we have to make the assumption that it's a roughly circular path. Okay, so if the path itself is relatively circular, then we know that it's moving a circular path around the Sun. We know the distance covered in a circle, right? By the time that it makes one revolution, it would cover a distance of about 2 pi times the radius between the two planets. So we know that our linear distance that we're going to cover is that. We now know our orbital velocity from the part before. Okay, so then if we use the relationship, if it's moving at a relatively constant velocity equals x over t, right? So in this case, my orbital velocity, my velocity that I've solved for from up above, should equal 2 pi r over t. So at this point, it's just a matter of them solving for t. Okay, so 2 pi r divided by the velocity if I rearrange this equation. Okay, so now it's just a matter of plugging in all the measurements we know, which ultimately leads us back to the original equation that I showed you up here. Okay, so regardless of whether you choose to do it in 2 steps, or again, the easiest way is you can remember this formula, but I know it's not always easy to do that. In any case, we're solving for the same t. Okay, and so when you solve for t, I'm going to go ahead and skip through the calculations. I'm running them short on time. But since when you solve for t, you should get that number to be about 78. I'm just going to go ahead and write this out, not in scientific notation. Right? So this is how many seconds we have, and then we need to make sure we convert that to years. So we need to divide it by 24 hours, 365 days, and then I know I did this out of order, but 60 minutes per hour, and 60 seconds per minute. So I need to make sure I convert that then from there.